Hello, welcome to Computer System Architecture, Operating System, and let me continue from the previous video slideshow. And today we're going to talk about most system use the computer system architecture itself, and most system basically use a single general purpose processor. This is usually a common case where we have one CPU basically, right? One processor on the computer, right? So they have one general purpose processor, right? But there are computers today with multiple processors, and uh, they are growing. A lot of systems are currently using this kind of things, right? They are also known as parallel system, tightly coupled system, right? And there's a lot of advantages of this. It increased throughput, it provides economies of scale, and some kind increased reliability, right? So in that sense, right? So you have more processors. Technically, you can do more things, provided the system is purely parallel, right? There's basically two types of multiprocessor system. We have asymmetric multiprocessing. That means each processor is assigned a specific task, or symmetric multiprocessing. That means each processor performs all tasks, right? So they either do all the process together in a symmetric form, or asymmetric. Each processor basically does different kind of jobs, right? Now we look at a symmetric multiprocessor architecture. We have two processors here, processor 0, processor 1. Right? It could be more processors depending on the how many processors we have. The CPU itself will have their own registers and cache, and both of them are connected to the main memory. Right? In a dual core design, right? So we heard about multi-core processors, right? So multi-core, multi-chip system basically contains all the CPU, right? So we have CPU core 0 or CPU core 1. They have their own registers, they have their own L1 cache, and they are connected to a L2 cache, right? So that's why you hear some computers have 2 caches, some computers have 3 caches, right? So in this case, one computer have one cache, but this one has L1 and L2, level 1 and level 2 cache, right? And both of the level 2 cache basically access the main memory, right? In a non-uniform memory access system, right, we have CPUs all having their own memory, right? So CPU 0, CPU 1, CPU 2, CPU 3, they are interconnected, and they all have their own memory, right? So this is good, but then from here we can see that they don't share the same memory, right? They have separate different memories here, right? So synchronization of this memory could be a difficult task, right? And there's also clustered system like multi-processor system that work together, right? So usually they share a storage, not memory, but a specific storage area network, right? Basically, one of the main ideas is to provide high availability, right? So if you have more computers in a network, it can handle failure very well, right? So if one computer is down, the others can still handle the specific work that needs to be done, right? So there are two types of clustering: asymmetric clustering or symmetric clustering, right? Asymmetric has one machine in hot standby mode. Symmetric one has multiple nodes running applications monitoring each other, right? So these clustered systems are usually used in high performance computing, right? It allows us to write parallel programming, parallel applications that would allow faster results, right? So if we look at this is how a cluster system would look like, right? So we have computer 1, computer 2, computer 3. They have their own CPU inside here, own memory inside here. They're connected between computers, and they share a data through a storage area network. So this is very different from this idea, right? Dual core design, or this one is one CPU, right? One chip. This one is clustered system is memory. Computers, right? These computers might be in different places altogether, right? For non-uniform one, this could be these are CPUs that are connected on the motherboard together, but maybe they are connected through a very high speed bus, right? this case, they're not connected at all except for maybe networking wires from one computer to another, right? So a PC motherboard basically looks like this. This is where you put DRAM, the processor itself, the PCI slots. So, depending on the motherboard, it may be support multiple CPU chips with a common bus that access the DRAM, or they have one CPU that already inside the CPU have multiple CPUs inside it, right? So we talk about those things, right? Now we're going to go into computer system environments, traditional ones, mobile, client server, peer-to-peer, cloud computing, and real-time embedded systems, right? Traditional standalone general purpose machine, you know, some of them are network computers with thin clients. They have web terminals. They are usually connected via wireless network or particularly LAN cables, right? Uh, and we have mobile ones like smartphone and tablets. They are connected via, basically 3G, and some of the popular ones like Google Android and Apple iOS. There's also the Huawei OS that's becoming popular, right? Okay. So there's another one, I think, for smartwatches as well, right? So client servers architecture is where we have server and we have client desktop, so multiple clients can access a server. This is usually the traditional method of doing stuff. There are also peer-to-peer system where there is no server. Every client basically communicates to each other in a peer-to-peer system. This is very popular application now for Napster, for Nutella, for other application like file sharing application like BitTorrent, right? Okay, today we also have cloud computing. Basically, we have servers and everything that's virtualized into a system into a server provided by big companies like Amazon, uh, Microsoft Azure, and even Google Node, right? So, cloud computing basically provides you to run servers in the public cloud, right? And it's available via the internet if you're willing to pay. Private clouds that you run on your own, basically run most of the time it's run by a company for their own use, or hybrid cloud system, right? Where they have both public and private ones, right? So some of the sensitive data is basically kept private, right? What cloud computing basically allows is SaaS, PaaS, and yes, right? So either provides software as a service where you can use word processor, for example, Google Docs is a SaaS system, or platform as a service, right? Software stack ready for application use, right? For example, a database server, or a infrastructure server or storage that's available on the internet to be used. And this is, for example, when you run your virtual private machine at VPS, right? So this is a cloud computing environment that you can deploy. How it would look like, everything will be on the internet. The customer can request for a cloud device, and it will create a virtual machine inside the cloud, right? So the user basically do not have access to the server. This is basically in the cloud. It access everything on the internet. This is basically managed by some company, right, that handles the cloud service, right? Some system are real-time OS. These are mainly used for real-time specific stuff. Some systems require very precise usage, and when it's concerned about time. So real-time OS have very well fixed time constraint. Right? Processing must be done within a specific constraint. These are mostly done for specific purposes, right? Maybe airplane operating system, or for security. For security, it requires things to run, and it needs to know whether some execution is successful within a given time frame, right? Other operating system are free and open source operating system. This pretty much used a lot. You've heard some of it: Linux, BSD, Unix, right? So you are welcome to explore some of the FSF, Free Software Foundation, and find out what kind of open source operating system that's available. There's a lot of it, right? So most of the operating system that you've used before, maybe in Windows or Mac, are very closed source, but there are also open source one like the Linux one, or the core of the Mac OS is actually open source based on the BSD Unix, right? So all right, so this end of the chapter 1. I hope to see you again in chapter 2, right? So for now, please look at the slides, review the slides, and please email me for any questions, right? Thank you very much. Please read on. There's a couple of sections after this for the kernel data structures and stuff, right? The good general knowledge. So please view it and try to understand what's going on and with the tables and kernel data structures. All right. I'll see you again, right? Chapter 2. Bye bye.